Moving medium is ordinary water. We placed a second stream of drops next to the one we were using a moment ago. This stream also has its inducer electrode and a pail for catching the drops. Now, however, there is no external source of voltage on either inducer ring. Rather, the rings are connected to the pails of the opposite streams, which causes them to charge spontaneously. The electrical breakdown makes it clear that with no excitation, this system generates about 20 kilovolts. Kelvin's water drop experiment demonstrates for us that not only does the motion generate the electric field, but that the field also has a strong influence on the motions. If we bear in mind that the major constituents of this experiment, air, water drops, and electric charges, are also in the atmosphere, it's not difficult to imagine that the drop dynamics have a lot to do with lightning. 3 streams, with each inducer electrode attached to the barrel of a neighbor. The alternating streams show that the fields are spontaneously building up. This time, the voltage of each pail increases in an oscillatory fashion. The arrangement of electrodes, water, and air is a 3-phase AC dynamo. The spreading drops illustrate this reverse effect. The like-charged drops tend to repel each other. Also, the pail has the same sign of charge as the drops, and the resulting electric force tends to prevent the collection of drops. The drops are deflected because of the electrical force on free charges. We have thought of this force as the total force on each drop. Actually, each elemental volume of the drop is subject to a force per unit volume. In slow motion, we see the effect of this force density in the distortion of the drops. In a material that is uniformly conducting, free charges tend to accumulate at interfaces, in regions where the conductivity changes abruptly. Thus, the charges on these drops are at the interfaces rather than in the interior.